This video is about calculating resultant force. A resultant force acting on an object will cause the object to accelerate in the same direction as the resultant force. We need to be able to find the resultant of two or more forces. First thing I want to go through is Newton's third law of motion. So for every action, there is an equal and opposite reaction. When one body exerts a force on a second body, the second body simultaneously exerts a force equal in magnitude and opposite in direction on the first body. So if you apply Newton's third law, if you push the wall, so forces always come in pairs. If you push on a wall, the wall is pushing back on you with the same force as you're pushing onto the wall. So it's in the opposite direction. So always come in pairs when you have a contact between the two things. So let's go through an example where we demonstrate Newton's third law. A person carrying a briefcase stands in a lift which is held by a cable. So we've got a lift, a person, cable holding a briefcase. Draw force diagrams for each of these four objects and then identify the pairs of forces that Newton's third law says can be modelled as equal and opposite. So first we have the cable, then we have the lift, then we have the person holding the briefcase. I should draw it because it's holding, it's not held by a spring. Let's just draw a briefcase like this. Okay, so let's go through what each one feels. So the briefcase feels the weight of the briefcase. So weight of B, weight of briefcase. And because the person is holding it, then there is a reaction force involved. So reaction, let's call it reaction 1. Okay, what does the person feel? So the briefcase feels the reaction force of the man pulling, or the person pulling it up. So the man feels the weight of the person. The person feels the weight of the person plus the reaction of with the briefcase. So the briefcase is pulling the person down. The person is standing on the lift, so the lift is pushing up. So this is a second reaction force, which is different to the other reaction force. And what does the lift feel? The lift feels its own weight, so weight of lift. Plus it feels the man or the person pushing down, which is equivalent to the force the person feels pushing up on the lift, so it's R2. The lift is being held by a cable, so there's tension on the cable, and the cable feels tension. Now, the ones that are the same are the reaction force that the man feels and the reaction force between the briefcase and the man. So this is Newton's third law. And the reaction from the lift and the man in contact. So this is Newton's third law as well. Okay, draw force diagrams thinking carefully about which forces are paired by Newton's third law. So a stack of 3 boxes sitting on a horizontal. So let's call this A, B, and C. So in this first scenario, we've got horizontal ground, we have the bottom box, we have the middle box, and then we have the top box. So we have ground, bottom box, middle box, and top box. So what does the top box feel? It feels its own weight, so weight of top box. It feels the middle box pushing up from it, so this is a reaction force 1. So middle box pushing it up. What does the middle box feel? The middle box feels its own weight, so weight of middle box. It feels the top box also pushing down on it, which is equivalent to what the top box feels pushing it up. So these are Newton's third law. The middle box also feels the bottom box pushing up. So this is a different reaction force, so reaction 2. What does the bottom box feel? The bottom box feels its own weight, so weight of bottom box. It also feels the middle box pushing down, which is equivalent to the middle box feels pushing up. So this is R2. So again, we have Newton's third law here. The bottom box also feels the ground pushing up, which is a different reaction force, so reaction 3. And the ground feels the bottom box pushing down, so it's reaction 3 here as well. So again, these come in pairs, so Newton's third law here. Okay, B. A man holding a box on the end of a string. The man is standing on a horizontal ground. So it's just a man holding a box in a string. Okay, so we've got the ground, we've got the man with the string with the box. So what does the box feel? And the box feels the weight of the box. Because it's being held by a string, the string feels tension, pulling it up. So the box feels tension. What does the man feel? The man feels the weight of the man. Plus it feels the tension from the string, pulling it down, so tension. Because the man is on the ground is pushing up, so the man feels a reaction force pushing it up, which is reaction 1. The ground feels the man pushing down, which is equivalent to the force the man feels pushing up from the ground, so reaction 1 there. So this is when Newton's third law happens. Okay, C. A woman holding a box on the end of a spring. The woman is standing on another box, which is on horizontal ground. So we've got woman on the box. Holding a hanging box on a string. Okay, so we've got ground, we've got box, we've got woman, and then we've got the hanging box. Okay, so what does the hanging box feel? The hanging box feels the weight of the hanging box, pulling it down, and the tension from the string pulling it up. The woman feels the weight of the woman, pulling it down, tension from the string pulling down. And because the woman is standing on the box, it feels the box pushing up, which is a reaction force, so reaction 1 pushing it up. The box feels the weight of the box, plus it feels the woman pushing down on it, which is equivalent to what the woman feels pushing up on her, pushing her up, so N, Newton's third law here. The box also feels the ground pushing up, which is a different reaction force, which is R2. The ground feels the bottom box pushing down, which is equal and opposite to what the box feels pushing it up. So Newton's third law. Okay, resultant force. A resultant force is obtained by combining all forces acting on a single object. So let's go through an example where we apply it. A book sits on a rough tabletop. So rough means there is friction on the table surface. The book is pushed horizontally by a force of 50 newtons. So pushed 50 newtons this way. Draw a diagram showing all the forces acting on the book and find the frictional side if the resultant force acting horizontally is 30 newtons. So if we're pushing it 50 newtons to the right, then friction is on the left. We have a reaction force at the top pushing up because it's sitting on a rough horizontal table. And obviously the book feels its own weight, so weight pushing down. So we know that resultant force is equal to 30 newtons. But resultant force is also equal to 50 newtons because it's moving this way by 30, it must be 50 takeaway friction. 50 takeaway friction. So that means 50 minus friction must be equal to 30, which means friction must be equal to 50 takeaway 30, which means friction must be equal to 20 newtons. What is the horizontal resultant force? We've been told the horizontal resultant force is 30 newtons. Which direction does it act? On to the right, so direction of 50 newtons. What is the vertical resultant force? Because it's not moving up and down, is 0 newtons. What direction does it act? No direction, as object is stationary vertically. Okay, what is the resultant force and indicate the direction in which it acts? So if it's 50 newtons to the right and 30 newtons to the left, then it'll be, because the right is bigger, it'll be 50 newtons to the right. 50 take away 30 is 20, so 20 newtons to the right. Okay, so in total in the next example, we've got 65 newtons on the right and 20 newtons on the left. So 65 take away 20 is 45 newtons. So 45 newtons to the right. Okay, in the third example, we've got 10 newtons going up and down, so it doesn't move vertically. So horizontally, we've got 30 newtons to the right, 20 newtons to the left. So 30 take away 20 is 10, so 10 newtons to the right. Last example, if you look at it horizontally, you've got 30 newtons to the left and 30 newtons to the right, so it doesn't move horizontally. Vertically, we've got 50 newtons going up, 10 newtons going down, so it's going to be going up. 15 take away 10 is 5 newtons, so 5 newtons going up. Newton's first law of motion. An object at rest will stay at rest, and an object with constant velocity will stay at constant velocity unless acted on by resultant force. Equivalently, if the resultant force is 0, the velocity is constant and the acceleration is 0. If the resultant force is 0, acceleration is 0, velocity is constant. That's all you need to know from that paragraph. If the resultant force in an object is 0, this state is called equilibrium. So an acceleration is 0, resultant force is 0, we're at equilibrium. If the resultant force in an object is non-zero, then the object's velocity will change, i.e. it will accelerate. Okay, so let's put this into practice. The diagram shows a particle acted on by a set of forces. Given that the particle is at rest, find the value of P and the value of Q. So acceleration is equal to 0 because the particle is at rest, which means resultant force is equal to 0. So that means horizontally, we know that 50 newtons is equal to P newtons, which implies P is equal to 50. If we resolve it vertically, then what we do know is 5Q must be equal to Q plus 10 plus 3P, which implies 5Q is equal to Q plus 10 plus P is 3 times 50, which means 5Q is equal to Q plus 160. So 4Q is equal to 160, which means Q must be equal to 160 divided by 4. Q must be equal to 40. Given that the particle in this diagram is moving with constant velocity, find the values of P and Q. So what we do know is when constant velocity, if we have constant velocity, we know acceleration is equal to 0, which implies resultant force is equal to 0. So that means horizontally we have 3p minus 2q is equal to 20. And vertically, oops, that's the wrong way around. So horizontally we have, oh, let's just relabel it. So vertically we have 3p minus 2q is equal to 20. And horizontally we have 2p plus q is equal to 25. So that's equation 1 and equation 2. Well, I want to make the q's the same. So if I multiply the second equation by 2, then I end up getting the first equation stays the same. 3p minus 2q is equal to 20. Second equation becomes 4p plus 2q, because we're doubling everything, is equal to 50. So let's call this 3 because we've only changed that one. So if we do, and that's still 1. So if we do 3, take away 1. If we do 3 take away 1, we end up p is 3 add 1, sorry. What am I doing? Because the q's are opposite signs, so we add 1. So we end up getting, when we add the two things together, we get 7p. 7p is equal to 70, which means p is equal to 70 divided by 7. P must be equal to 10 newtons. Okay, and it says find the value of q now. So we're using which one? Using 1. We end up with 3p minus 2q is equal to 20, which implies 3 times 10 minus 2q is equal to 20. 30 minus 2q is equal to 20, which means 2q is equal to 30, take away 20. 2q is equal to 10, which means q must be 10 divided by 2, which is 5 newtons. Okay, a lift has weight 1,960 newtons and begins to move up a lift shaft under a resultant force of 1,000 newtons. Find the tension in the cable if the lift is empty. So we've got a lift. Its weight is 1,960. And we know obviously it's being held by a cable, so it's going to be tensions also involved. The resultant force, so it's moving up, so direction going up. Resultant force is equal to 1,000 newton. Okay, so we also know the resultant force must be equal to, because it's moving up, it must be equal to forces move, pulling it up, take away forces pulling it down. So that means T take away 1,960 newtons, which means 1,000, which implies 1,000 must be equal to T take away 1,960, which means T is equal to 1,000 plus 1,960, which means T is equal to 2,960 newtons. Another lift has weight 5,880 newtons and begins to move up the shaft under a resultant force of 2,000 newtons. If the cable is exerting a tension of 8,600 on the lift, find the reaction force of the man in the lift on the lift floor. So we've got a man on the lift. Okay, so we've got the cable, we've got the lift, and then we've got the man. So the lift has weight 5,880. So 5,880, and begins to move up the shaft. So it's moving up. So just remember it's moving up under a resultant force of 2,000. If the cable is exerting a tension of 8,600, so we know it's 8,600 here. And 8, the undo, so this tension is 8,600. So what does the man feel? The man feels the weight of the man, so weight of man. And the man also feels a lift pushing it up, which is reaction 1. So the lift feels its own weight plus the reaction of the man. So there. So we just set it up. So we know resultant is equal to, everything's been labeled so we can answer the question. Resultant force is equal to 2,000 newton. But it's also equal to, for the lift, is equal to 8,600. It's also equal to 8,600 because it's moving up. So forces going up, acting up, take away forces acting down, acting downwards. So 5,880 take away R1. So that means 2,000, which is the resultant force, must be equal to 8,600 take away 5,880 take away R1, which is the reaction force of the man in the lift on the lift floor. So if I rearrange it, I get R1 must be equal to 8,600 take away 5,880 take away 2,000, which works out to be 720 newtons. A car is moving along a horizontal level road. The car's engine provides a constant driving force. The motion of the car is opposed by a constant resistance. A. Modeling the car as a particle, draw a force diagram to show the forces acting on the car. So if I think this is the car, which is on a horizontal ground, so the car obviously feels its own weight. Because the car is touching the ground, road, then there must be a reaction force that's pushing it up. There is a driving force pushing it forward. And there's a resistance as well, which is acting in the opposite way of the driving force. So resistance. Okay, given that the resultant force is acting on the car is 4,200 newtons. So resultant force is equal to 4,200 newtons in the direction of the motion. So it's going in this direction by 4,200 newtons. And that the magnitude of the driving force is 8 times the magnitude of the resistance force. So if the resistance force is F, then driving force is 8 times F. Calculate the magnitude of the resistance. So that means because the resultant force is equal to 4,200, it's moving to the right. So the resultant force is also forces acting to the right take away forces acting to the left, which is 8F take away F. So that means we've got 8F take away F is equal to 4,200, which means 7F is equal to 4,200, which means F is equal to 4,200 divided by 7, which is F is equal to 600 newtons. So the magnitude of the resistance is therefore magnitude of resistance is equal to 600 newtons. A man with a parcel stands in a lift. If none are moving and the weights are 29.4 newtons, 539 newtons, and 19,600 newtons as appropriate, find the magnitude of the tension in the parcel string, the force exerted by the man on the floor of the lift, and the tension in the lift cable. So we've got a man on a lift with a parcel on a string. Okay, so we have the lift. We've got the man, and then we've got the parcel. So what does the parcel feel? The parcel feels its own weight. So weight of parcel pushing it down, which is equal to, we can just write it down what it is, which is 29.4 newtons. And then pulling it up is the tension from the string. The man feels its own weight, which is 539, plus the tension, obviously, pulling it down. So let's call it tension 1, because there's another tension involved. The man also feels a reaction force from the lift pushing it up, so reaction force there. The lift feels obviously its own weight, which is 19,600, plus the reaction force from the man standing on top of it, so the man pushing down. And then there's a tension which is different to the other tensions, the tension on the cables. Okay, so if we look at the lift, so looking at the, first we need to find the tension in the parcel string, okay? Because no one is moving, we know acceleration is equal to 0. Okay, so that means for the parcel string. If we resolve it vertically, then what we do know is T1, because it's not moving, T1 must be equal to 29.4 newtons. So therefore, tension in parcel string is equal to 29.4 newtons. If we look at the man, if we resolve the man, so looking at the man again vertically, we know R, because then again he's not moving, forces acting up must be equal to forces acting down, which is 539 plus T1, which is equal to 539 plus 29.4, which is equal to 568.4 newtons. Therefore, force, because it's the same, so force exerted by the man on the floor of the lift, because it's the same as R here. So if you want to see Newton's third law, so it must be equal to 568.4 newtons. Now, if we look at the lift and resolve the forces vertically, then we know T2 must be equal to, because it's not moving again, T2 must be equal to forces acting downward, which is 19,600 plus R, which is equal to 19,600 plus 568.4, which is equal to 20168.4 newtons. Therefore, tension in lift cable must be equal to 2,168.4 newtons. Okay, last question. The same lift now starts to move due to an increase in the lift's cable tension to 22,226.4, causing a resultant force of 2,000 on the lift and the resultant of 55 newtons on the man. Find the new tension in the parcel string. Now, because the tension has increased, it means it's going to move up, because there's more force pulling it up and it's moved, which means it must be moving up. So that means now we've got the lift. We know the tension now, which is 22,226.4 newtons pulling up. So we know, so we've got the man and we've got the parcel. So what we do know is the parcel still has weight, obviously 29.4. We still have tension pulling it up, but it's going to be a new tension because everything else has changed. So let's call it tension T, because now we don't have a T2 now, because we already know the second tension value. The weight of the man is 539 plus the tension pulling the man down. The reaction we don't know because it's changed now, but we do know the man is moving with a resultant of 55 newtons up. So man is moving up with a resultant of 55 newtons. The weight of the lift is still the same, which is 19,600. Feels the reaction from the man, and the lift has a resultant of 2,000 moving up. So if you look at the lift and we resolve it vertically, then what we do know is, because it's moving 2,000 up, resultant must be equal to 2,000 must be equal to forces acting up, which is 22,226.4, take away 19,600, take away R, which means R is equal to 22,226.4, take away 19,600, take away 2,000, which is equal to 626.4 newtons. So now that we worked out what R is, we can look at the man and resolve the forces vertically. Then we know 55 newtons, which is the resultant force, must be equal to the forces acting up, which is R, take away 539, which is the force acting down, take away T. which means 55 must be equal to 626.4, take away 539, take away t, because we know r is equal to 626.4. If I rearrange it, t must be equal to 626.4, take away 539, take away 55, which means T is equal to 32.4 newtons. Therefore, tension in parcel string is equal to 32.4 newtons.